In 1971, scientists put an atomic clock on a plane and flew it around the world. When it landed, they compared it to an identical clock that stayed on the ground. The result? The flying clock was slower, by billionths of a second, but measurably slower. Time had literally moved slower on the plane. This wasn't a malfunction. This was time travel. Real, confirmed, repeatable time travel into the future. Einstein predicted it. Physics allows it. And we've done it. The question isn't whether time travel is possible anymore. The question is, how far can we push it? And what happens when we try to go backward? Time travel isn't science fiction. It's science fact. Every GPS satellite orbiting Earth experiences time differently than you do on the ground. They're moving fast and experiencing weaker gravity, so their clocks run faster. By microseconds per day. If GPS systems didn't account for relativistic time dilation, your navigation would be off by miles within hours. Your phone corrects for time travel every time you check directions. You just don't notice it. But it's happening. Einstein's theory of relativity, both special and general, predicted all of this over a century ago. And every prediction has been confirmed. Time is not constant. It's flexible. It bends. It stretches. It slows down and speeds up depending on speed and gravity. Which means time travel into the future is not only possible, it's inevitable. The faster you move, the slower time passes for you. The question is just, how fast do you need to go? Let's start with special relativity. In 1905, Einstein published a paper that changed everything. He showed that time and space are linked, space-time, and the faster you move through space, the slower you move through time. This is time dilation. Here's the formula. If you're moving at a significant fraction of the speed of light, time slows down for you relative to someone who's stationary. It's not an illusion, it's real. If you traveled on a spaceship at 99% the speed of light for 1 year and then returned to Earth, you'd have aged 1 year. But decades would have passed on Earth. Everyone you knew would be older or dead. You've traveled into their future. This is the twin paradox, though it's not really a paradox. It's just relativity. One twin travels at near light speed. The other stays home. When the traveling twin returns, they're younger. The math works. The physics is solid. We've tested it with particles. Muons created in Earth's upper atmosphere by cosmic rays should decay before reaching the ground. But they don't. Because they're moving so fast, time slows down for them. From their perspective, the journey is shorter. From our perspective, they live longer. Time dilation in action. But there's a problem. The speed of light is really, really fast. About 300,000 kilometers per second. No human-made object has ever come close. The fastest spacecraft we've ever built, Voyager 1, is moving at about 17 kilometers per second. That's 0.006% the speed of light. At that speed, time dilation is negligible. You'd need to travel at a significant fraction of light speed to experience meaningful time travel, and that requires enormous amounts of energy. To accelerate a 1 kilogram object to 90%, the speed of light requires more energy than humanity produces in a year. To accelerate a spaceship with people? Inconceivable with current technology. So forward time travel via speed is theoretically possible, but practically out of reach. For now. Then there's gravity. General relativity says that massive objects warp space-time. The stronger the gravity, the slower time moves. This is gravitational time dilation. If you stand at the base of a mountain, time passes slightly slower than at the peak. The difference is minuscule, nanoseconds, but it's measurable. And near extremely massive objects, the effect is dramatic. Near a black hole, time slows down enormously. If you could hover just outside a black hole's event horizon, time would pass so slowly for you that you could watch the universe age. Minutes for you could be years, decades, centuries outside. When you left and returned to Earth, you'd find yourself in the distant future. This is exactly what happened in the movie Interstellar, though exaggerated for drama. The planet near the black hole Gargantua experienced extreme time dilation. 1 hour there equaled 7 years on Earth. The physics is real. The numbers are sci-fi, but the principle is sound. In fact, we've observed this with GPS satellites. They orbit about 20,000 kilometers above Earth, where gravity is weaker. Clocks there run about 45 microseconds per day, faster than clocks on the surface. Simultaneously, they're moving fast, which makes their clocks run about 7 microseconds per day, slower due to special relativity. Net effect, 38 microseconds per day faster. Without correcting for this, GPS would accumulate errors of several kilometers per day. Engineers program the satellites to adjust their clocks. They're compensating for relativistic time travel every single day. So forward time travel is real and easy, relatively speaking. Just go fast, or hang out near a massive object. But what about backward time travel? Can you go into the past? This is where things get weird and controversial. According to Einstein's equations, backward time travel might be possible, but it requires exotic conditions. Let's talk about wormholes. A wormhole is a tunnel through space-time connecting two distant points. Think of space-time as a sheet of paper. Normally, traveling from one point to another means moving across the surface. But if you fold the paper and poke a hole through, you can connect the 2 points directly. That's a wormhole. Einstein and physicist Nathan Rosen described them in 1935. They're called Einstein-Rosen bridges. Do they exist? We don't know. The equations allow them. But we've never observed one. And even if they exist naturally, they'd be microscopic and unstable, collapsing instantly. But here's the trick. If you could create a stable wormhole, you could use it for time travel. Here's how. Imagine you create a wormhole with two ends. Call them A and B. Initially, both ends are in the same time. Now take NB and accelerate it to near light speed, then bring it back. Due to time dilation, less time passes for B than for A. Now the two ends are at different times. If you enter end A, you emerge from end B in the past. You've traveled backward in time. Physicist Kip Thorne worked out the math in the 1980s. It's theoretically possible. But there are problems. Huge problems. First, you need a stable wormhole. That requires exotic matter with negative energy density, something that repels gravity instead of attracting it. We've seen hints of negative energy in quantum mechanics, Casimir effect, Hawking radiation, but creating enough to stabilize a wormhole? That's beyond anything we can do. Second, even if you had a wormhole, using it for time travel creates paradoxes. The most famous is the grandfather paradox. You travel back in time and kill your grandfather before your parent is born. Now you're never born. But if you're never born, you can't travel back to kill him. So, he lives. So, you're born. So, you travel back and kill him. It's a loop with no resolution. How do you escape this? One solution: the Novikov self-consistency principle. Proposed by physicist Igor Novikov, it says that any action you take in the past must be self-consistent. You can't change the past because your actions were always part of it. If you try to kill your grandfather, something always stops you. The gun jams. You miss. He survives. The timeline is self-correcting. You have free will, but only within actions that don't create paradoxes. It's determinism with extra steps. Another solution: the many worlds. Interpretation. When you travel back and kill your grandfather, the timeline splits. In one branch, he dies, and you're never born. But that's a different timeline. The original timeline, where you were born and built the time machine, still exists. You've just created a parallel universe. There's no paradox because you're not changing your past. You're creating a new branch. This is consistent with quantum mechanics, but it raises questions. Are you stuck in the new timeline? Can you return to the original? Do you care if the grandfather you killed is your grandfather, or just a version in a parallel universe? Then there's the chronology protection conjecture. Proposed by Stephen Hawking, it suggests that the laws of physics conspire to prevent time travel to the past. Whenever you try to create a closed time-like curve, a path through spacetime that loops back on itself, quantum effects destabilize it. Virtual particles circulating through the loop create infinite energy, density, destroying the wormhole before you can use it. Hawking joked that this is nature's way of making the universe safe for historians. The math suggests he might be right. Every theoretical time machine we've proposed runs into this problem. The universe doesn't seem to like backward time travel. But there are loopholes. In 1949, mathematician Kurt Gödel found a solution to Einstein's equations where the entire universe rotates. In a rotating universe, you could travel along a curved path and return to your starting point in the past. It's called a Gödel universe. Problem? Our universe doesn't rotate, at least not as far as we can tell. In 1974, physicist Frank Tipler proposed the Tipler cylinder, an infinitely long, incredibly dense cylinder spinning at near light speed. If you flew a spaceship around it in a spiral path, you'd travel back in time. Problem? Infinitely long and incredibly dense. We can't build that. In 1991, physicist Richard Gott proposed cosmic strings, hypothetical defects in spacetime left over from the Big Bang. If two cosmic strings passed by each other at high speed, their combined warping of spacetime might create closed time-like curves. Problem? We've never detected a cosmic string. They might not exist. Every proposed time machine has the same issue. It requires exotic conditions we can't create or observe. And even if we could, quantum mechanics might destroy it. So here's where we stand. Forward time travel is real. We've done it. It's just a matter of going fast or hanging out near massive gravity. Backward time travel? Allowed by equations. Probably impossible in practice, but we can't rule it out completely. Now let's talk about implications. If backward time travel is possible, even in principle, things get philosophically weird. Does the past exist? In the block universe view, favored by many physicists, past, present, and future all exist simultaneously. Time is just another dimension, like space. You can move through it. The past isn't gone. It's just somewhere else in space-time. You could, in principle, travel there. But if that's true, then everything that will ever happen has already happened. The future is fixed. Free will is an illusion. You're just moving along a predetermined path through the block. This is eternalism. The alternative is presentism. Only the present exists. The past is gone. The future hasn't happened. Time is the unfolding of possibilities. But if only the present exists, how can you travel to the past? It's not there. You'd be traveling to nothing. Most physicists reject presentism because relativity breaks it. Simultaneity is relative. There's no universal now. Your present is different from someone moving at a different speed. So which present is the real one? Block universe avoids this problem, but it makes time travel seem inevitable and free will impossible. Then there's causality. If you can travel to the past, you can create causal loops, events that cause themselves. The classic example: a time traveler goes back and gives Shakespeare a complete works of Shakespeare. Shakespeare publishes them. Centuries later, The time traveler finds the book, takes it back, and gives it to Shakespeare. Where did the information come from? No one wrote it. It just loops. This is called a bootstrap paradox or ontological paradox. It doesn't violate logic, but it violates our intuition about causation. Things need origins, but in a causal loop, there is no origin. The effect is its own cause. Physics allows this. Our brains hate it. What about practical uses? If we could time travel, what would we do? Historians would love it. Go back and witness actual events. But you couldn't interact. Any interaction risks changing history, unless the Novikov principle applies, in which case, you were always there. Your presence is part of the historical record. You just didn't know it. Scientists could observe the past directly. Watch evolution. Witness the Big Bang. But again, no interference. Maybe we'd use it for information. Go to the future, see which stocks succeeded, come back, invest. But if many people do this, stock markets become unpredictable. Everyone's acting on future information, which changes the future, invalidating the information. Or maybe we'd use it for correction. Go back and prevent disasters, stop assassinations, prevent wars. But every change has consequences. You save one person, and it ripples. Maybe someone they inspired never gets inspired. Maybe a technology is delayed. Maybe something worse happens. This is the butterfly effect. Small changes in the past cause massive changes in the future. You can't control it. You might make things worse. Some physicists think we've already encountered time travelers. Where are they? If time travel is possible, and humans eventually discover it, then the past should be flooded with tourists from the future. Yet we don't see them. Why? Maybe time travel is impossible after all. Maybe it's possible, but so difficult that no one bothers. Maybe they're here but hiding. Maybe they can only travel to moments after the invention of the time machine. You can't go further back than the machine's creation. Maybe traveling changes the timeline, so they're in a different branch. Or maybe, and this is the unsettling one, we're in a branched timeline created by a time traveler's interference. The original timeline is gone. We're the altered version, and we'd never know. Stephen Hawking once held a party for time travelers. He sent invitations after the party. The idea, if time travel is possible, future people would receive the invitations, travel back, and attend. No one showed up. Hawking took this as evidence that time travel to the past is impossible. Or maybe the party just wasn't interesting enough for future humans. Or maybe they did show up, but remained invisible. Or maybe, here's a fun one, maybe a time traveler did show up, and their presence altered the timeline such that Hawking never held the party, creating a paradox that collapsed into a timeline where no one attended. Who knows? Here's the thing. Time travel breaks our intuition because it breaks causality. We're used to cause preceding effect. You turn the key, then the engine starts, not the other way around. But time travel allows effect to precede cause, or for cause and effect to loop. It's logically consistent, but feels wrong. And maybe that's the real answer. Maybe the universe doesn't allow backward time travel, not because of energy requirements or stability issues, but because causality is fundamental. More fundamental than space, more fundamental than time. If causality can't be violated, then backward time travel can't happen. Not won't. Can't. That's the chronology protection conjecture. The universe won't let you break cause and effect, because if you did, reality would become incoherent, and reality doesn't like incoherence. So, where does that leave us? Forward time travel. Possible, confirmed, just needs speed or gravity. Backward time travel. Equations allow it, but probably impossible due to quantum instability and causality constraints. The catch? You can visit the future, but you can't come back. You can watch the universe age, but you're stuck in the flow. Time only goes one direction for us. Forward. Always forward. Maybe that's for the best, because if we could change the past, we'd probably break everything. Humans are bad enough at handling the present. Imagine giving us access to all of history. We'd undo every mistake, erase every regret, rewrite every outcome, and in the process, we'd erase ourselves. The timeline would fracture. Cause and effect would collapse. Reality itself might unravel. Maybe the universe is protecting us from ourselves, keeping the past locked. Not because it's gone, but because we can't be trusted with it. But here's the kicker. Time travel to the future is one way. You can't undo it. Once you've jumped forward, everyone you knew is gone. The world has changed. You're a stranger in a strange time. Is that worth it? Astronauts on the International Station experience tiny amounts of forward time travel, milliseconds due to speed and weaker gravity. Would you take a spaceship journey that aged you 1 year while Earth aged 100? You'd see the future, but you'd lose everyone you love. Is knowledge worth that price? Is curiosity? Maybe, for some, but it's permanent. There's no reset button, no going home. Time only flows one direction, and once you step into the current, you can't swim back. You can only drift forward, into the unknown, into a future you can never leave. That's the catch. Time travel is possible, but it costs everything.